Hello students, Jai Swaminarayan. I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Gandhinagar. I am the subject matter of Power System 2 subject, which is in the 5th semester Electrical Engineering, and GTU subject code of this subject is 3150911. Students, we are currently discussing the chapter number 5, that is symmetrical components, and today we are having a lecture number 2, and in which we are going to discuss the topic number 5. So before we start this topic, we will remember the what we have learned in the previous lecture. So in previous lecture we have discussed the topic number 1, that is we discussed the detailed introduction of the symmetrical components, and why the symmetry means why we have the methods which are applicable and which are not applicable to solve such symmetrical component, means symmetrical folds. And then after we have discussed the Foscue's theorem for positive sequence, negative sequence, and the zero sequence component of the symmetrical components. And then after we have discussed the complex operator for which work as a multiplier for different units of the power system. And then after we have discussed the synthesis of unsymmetrical phasors from their symmetrical components, in which we have discussed the positive sequence, negative sequence, and the zero sequence components with its phasor and detailed derivation. Now students, we are having, this is lecture number 2, and in which we have the topic number 5, that is symmetrical component of unsymmetrical phasor. So let us discuss how the symmetrical component which can derive from the unsymmetrical phasor. Now symmetrical component of say unsymmetrical phasor, in which we are having this equation that we have already derived. So let us consider a set of voltage phasor that we have already discussed, that VA, VB, and VC, which are the unbalanced, and we are finding the solution for this. And according to the Foscue's theorem that we have applied for the positive sequence, negative sequence, and zero sequence component, and we have derived these three equations, in which VA1, VB1, and VC1 are the positive sequence components, VA2, VB2, and VC2 are the negative sequence component, and VA0, VB0, and VC0 are the zero sequence component of the given system. So for that, the equations are for VA, VB, and VC, and where VA1 is equal to VA2 plus VA0. So we are having this VA1, VA2, and VA0. So we are making VA1 as a subject. So VA2 plus VA0 are the symmetrical components of the phase A, and VB1 plus VB2 plus VB0 are the symmetrical components of the phase B, and VC1, VC2, and VC0 are the symmetrical components of the phase C. And we can write this equation in terms of alpha operator. So for that VB1 we can write the alpha square VA1. For VB2 we can write the equation alpha into VA2. Then we can write the VB0 is equal to VA0. So that VC1 is equal to alpha A1, and VC2 is equal to alpha square A2, and then VC0 is equal to VA0. So these are the equations that we can write from the alpha operator. And the equations, the 5.1, then we are rewriting over here VA1, VB2, VA2, and VA0. So VA is equal to VA1, VA2 plus VA0, where VB is equal to alpha square VA1 plus alpha A2 and plus VA0, and VC is equal to alpha A1 VA1 plus alpha square VA2 plus alpha plus VA0, that we have already derived, and we are putting the value of the respective components. So from that we can write the we can write this equations in terms of the matrix. So above equation can be written in terms of matrix, say VA, VB, and VC will become one matrix. And then after we have the there is no operator over here, only in this term and this term we have the operator alpha. That's why in the first equation we will having 1 1 1, then this is alpha square alpha and 1, then alpha square and 1. So this is the matrix that we can form from this above equations 5.3, 5.4, and 5.5. And then after we can write that VA1, VA2, and VA0 are the components of the given system. Now from that we can write that V at means matrices V at P into A into V at S. So where V at P is equal to VA, VB and VC, which defines the vector of original phasor which are having balance or unbalanced, and the V at S is at S is VA1, VA2 and VA0, so vector of symmetrical component. So we are having means reduction of this means matrix with this the name V at P and V at S, and then after we have the A, that is 1 1 1 alpha square alpha and 1 alpha alpha square 1. This is called the transformation matrix. So yes, we can write Vp is equal to A into Vs. So from that, if we make the subject Vs is Vs, then that the equation will become A inverse into Vp. So the sequence component of A inverse into the original phasor and Vp. So this is the equation that we can write from this. Yes, where Vs is the sequence component and Vp is the original phasor. Now where A inverse is, we can apply A inverse over here. So then 1 1 1 alpha square alpha 1, then alpha alpha square 1 inverse, then that will become 1/3 of 1 alpha alpha square, then 1 alpha square alpha, and then 1 1 1. So this is how we can make the A inverse, where A inverse is adjoint of A. So we can find the adjoint of A and divide by mod A. So this equation, this matrix will become like this. So the equation 5.111 we are writing over here again. So VA1, VA2 and VA0 is equal to 1/3 of this what we have derived, 1 alpha alpha square, 1 alpha square alpha, and then 1 1 1. Then the next equation is VA, VB and VC. So from that we can write the equation Va1 is equal to 1/3 of Va alpha Vb plus alpha square Vc. We are just multiplying the values over here with this matrix. So we are writing this equation Va2 is equal to 1/3 uh, into Va plus alpha square Vb plus alpha Vc, and Va0 is equal to 1/3 Va plus Vb plus Vc. So from the equation 5.12, 5.13 and 5.14 give the relation for the obtaining symmetrical components of the original phasor. So for original phasor, if you want to find the symmetrical components, then we can use this equation to solve the given system. And the symmetrical component transformation is also applied, so for the set of current in same manner of the voltage. So yes, we can write the I at P is equal to A and I at S, where I at S is equal to A inverse of Ip. We can write this equation from the I equation from the voltage equation. So I at P is equal to IA, IB and IC, and I at S is equal to IA1, IA2 and IA0. Similar to the voltage equation, we have just replaced with the currents of the given system or given network, where IP is the phase current and the IS is the symmetrical component of the sequence current, and where IS is equal to A inverse into IP. This is the equation that we have written from the voltage equation, and from that we can write the equation for the IA1, I2 and IA0. So we are taking matrix of IA1, I2 and IA0, and it will become 1/3 of 1 alpha square alpha, 1 alpha alpha square, then 1 alpha square alpha, then 1 1 1 into multiply with IA, IB and IC. Now symmetrical components of the phasor we are writing over here similarly to the voltage equation. IA1 is equal to 1/3 of IA plus alpha IB plus alpha square IC, and IA2 is equal to 1/3 IA plus alpha square IB plus alpha IC. We are just multiplying these two vectors with each other, and IA0, then 1/3, that will become IA, IB and IC, because all three terms are 1. So yes, figure 5.8 which is showing three-phase system with neutral. So over here you can see that we are having three-phase system which the neutral is connected over here. The neutral current is IN. So the sum of the three line voltage will always be 0. Yes, because it is meeting at this point, so that's why magnitude of the each current will be same, so that's why it will be 0. Therefore the zero sequence component of the line is always 0. So that's why VABC is equal to 1/3 VAB plus VBC plus VCA. So we can write this equation from this diagram. So and the sum of the phase voltage, so the line to neutral may not be 0. Yes, for the phase voltage, line to neutral may not be 0, because we will get the value of phase voltage. So the neutral wire current are, say, IA0 is equal to 1/3 of IA, IB and IC, or we can say we can write the IN by 3. So this is the equation that we can derive from this solution. And in absence of the neutral connection, the zero sequence line current is always 0, so that's why ia0 is equal to in by 3 is equal to 0. So this is how we can solve the symmetrical components of the, say, unsymmetrical phasor from the with the help of matrix equation of the given system. Now let us discuss the next topic of this presentation. So this is our topic number 6, that is power in terms of symmetrical component. So yes, we know that power, we are having a power in say power system is active power, reactive power, and the apparent power. So let us discuss this power in terms of the electrical component. So yes, power in terms of symmetrical components, we can write the equation for the apparent power as a single phase is equal to P plus jq, where P is the active power, Q is the reactive power, S is the apparent power. And we can write the equation S is equal to, means P is equal to V into I, so we can take S is equal to V into I conjugate, that we have already discussed in the previous chapters. Now for the three phase, that is P plus jq, so that will be VA IA conjugate, VB IB conjugate, and VC IC conjugate. So where VA, VB, and VC are the voltages to the neutral at the terminal, and the IB and IA, IB, and IC are the current flowing into the system in three lines. So yes, we can write the equation in terms of matrix over here. So S is equal to VA, VB, and VC into IA, IB, IC conjugate. So VA, VB transpose into IA, IB, IC conjugate. So where subscript T stands for the transposition of the matrix, we are taking row to column, column to row. So yes, VA, VB, and VC was horizontal, it will become vertical. So S is equal to AV transpose into AI conjugate. So yes, V transpose into A transpose into A conjugate into I conjugate. So reversal means rule of the matrix algebra is applied over here. So the equation that we get 5.24 and 5.25 by giving the reversal rule of the matrix algebra. So let us discuss what is A. Is the transpose of the say transformation matrix A is obtained by putting the column of A as the row for of the A transpose. So yes, that we have done over here. A is equal to 1 1 1, then 1 alpha square alpha, then 1 alpha alpha square. So A transpose will become 1 1 1, 1 alpha square alpha, and 1 alpha alpha square is equal to A. So the A conjugate that we apply over here, then 1 1 1, 1 alpha square conjugate, alpha rest conjugate, and 1 alpha conjugate into alpha 2 conjugate, alpha raised to 2 conjugate. But alpha conjugate is equal to alpha raised to 2, and alpha 2 conjugate is equal to alpha, that we have already derived in the previous lectures. So A conjugate is equal to 1 1 1, 1 alpha alpha square, and 1 alpha square alpha. So this is the matrix that we can form from for applying this rule, by applying this rule. So A transpose into A conjugate, so A transpose that we get in the previous slide, that is 1 1 1 alpha square alpha, then 1 alpha alpha square, and the A conjugate that we get 1 1 1, 1 alpha alpha square, 1 alpha square alpha. So we are multiplying this two and will get the 3 0 0 0 3 0 and 0 0 3. So that we have all the equation related to this. So yes, 3 into 1 1 1 diagonal matrix, so it is called 3 into U, and U is called the unit matrix because all the diagonal elements are 1 and rest of the elements are 0. So that's why it is called unit matrix. And substituting the value of A transpose into A conjugate in equation 5.25, so we are putting the value of over here. So S is equal to 3 into VA0, VA1, and VA2, and IA0, IA1, and IA2. So thus the complex means three phase power is given as say VA into IA conjugate plus VB into IB conjugate plus VC into IC conjugate. So over here we are putting just over here 3 VA0 IA0, 3 VA1 IA1, and 3 VA2 IA2. That is the complex power of the, means the three phase power for the given system. So this is how we can solve the parameters, or means the terms means power in terms of the symmetrical components. Now let us discuss the example which are based on this the topics that we have covered till today in chapter number 5. So we are starting with the example number 1. The current in the three-phase unbalanced system. So we are having three-phase unbalanced system having current IA, IB and ICs are given over here. That is, IA is 12 plus J6, IB is 12 minus J12, and IC is minus 15 plus J10. All are in ampere. So this phase sequence, the phase sequence is ABC. So we are taking ABC phase sequence and calculate the positive, negative and zero sequence components of the current. So let us write the equation over here from the given data. So the solution is IA is equal to 12 plus J6. So this is the A plus JB form. So we are converting this is in R angle theta. So IA will become 13.41 at angle 26.56 degree, and where IB is equal to 12 minus J12. So for this complex we are having R angle theta is 16.97 at angle minus 45 degree, and IC is minus 15 plus J10. So the for this A plus JB, the R angle theta is 18.0281 at angle 146.31. Now calculation of the zero sequence current. This is the equation that we have derived in the previous case. That is, IA0 IB0 is equal to IC0 is equal to 1/3 of IA plus IB plus IC. Now we have all the values of IA, IB and IC. Just put the values over here. We will get the we will get the value of the zero sequence current. That is 3 plus J 1.333 ampere. So now let us discuss the point number 2, that calculation of the positive sequence current. So for IA1 we are having this equation. IA1 is equal to 1/3 of IA plus alpha IB plus alpha square IC. So yes, we can have the value of all the parameters. That is 1/3 of say IA is 12.J6 and alpha is 1 at angle 20, because this is the positive sequence and all are having 120 degree phase difference. So alpha will become 1 at angle 140, then 1 at angle 240, and 1 at angle 360 will become 1. So that's why it is mentioned over here it is 1. So by putting the values of IA, IB and IC, and by solving all the terms related to this given data in the example, we will have the IA1 that is 1/3 into 32.55 plus J 30.382. This is the A plus JB form. The R angle theta form of this given means derived value is 14.842 at angle 43.02 degree. And this is the value of, this is the current. That's why the unit is in ampere. Now for the IB1 we are having the equation that is alpha square IA1. Now alpha square is 240, so 1 at angle 240 square, 1 at angle 240 multiplied with IA1, and IA1 is that is given in the that we have derived from this. So that is IA1 is 14.842 at angle 43.02. So yes, after solving this two, we'll have the value of in R angle theta form, that is 14.842 at angle 283.02, and the A plus JB form of this IB1 is 3.343 minus J 14.46 ampere. Now from that value of alpha IA1, we can calculate the value of IC1. So IC1 is alpha IA1. So IC1 is the parameter number 1. So it is at 1 at angle 120. So yes, 14 it is multiplied with for 14.842 at angle 43.02 degree. So IC1 will be will after solve this will have IC1 is 14.842 at angle 163.02, and the A plus JB form of IC1 is 14.90 plus J 4.33 ampere. Now we are calculating the calculation of negative sequence current. So for negative sequence current, this is the equation again that we have derived in the previous case, that IA2 is equal to 1/3 of IA plus alpha square IB plus alpha IC. Now we have all the values which are given over here. So by putting that values, we will have the value, we will have the solution of IA2 in terms of A plus JB, that is minus 1.85 minus J 5.48. So this is the A plus JB form. So we can convert this A plus JB form into R angle theta. So R angle theta of this value means given value is 5.6 5.766 at angle minus 108.72 ampere. Now IB2 is equal to alpha I2. Again, this is what we have derived in the previous theory. So alpha I2, so we have the value of IA2, alpha IA2. So IA2 is this and alpha is 1 at angle 120. So the value that we get is 5.766 at angle 11.28, and A plus JB form of this R angle theta is 5.56 plus J 1.127 ampere. And then after we can calculate the IC2, where IC2 is alpha square into IA2. So yes, this is the equation again that we have what we have derived in the previous theory. So 1 at angle 240, this is square, so that's why it is 240, and it is multiplied with IA2, and IA2 value of the IA2 is 5.766 at angle minus 108.72. So the IC2 will become 5.766 at angle 131.28, and this is the R angle theta form. Now A plus JB is minus 3.80 plus J 4.33 ampere. So this is how we can solve the example for the positive sequence, negative sequence, and zero sequence component. Now let us discuss the example number 2, so that will be more clear to you how to solve this example, and such kind of examples are frequently asked in your GTU exam. So please prepare it very well, and go through it very with proper presence of mind. So let us start with the second example. So that is one conductor of free phase line is open. So yes, in this diagram it is shown over here. You can see that the C conductor is open. The current flowing to delta connected load. So this is the load which is connected over here through a line A is 10 ampere at angle 0, and with the current in A as reference, and assuming line C is open. So yes, we are assuming this line is open, and find the symmetrical component of the line current. So we need to find out the symmetrical component of this line current which is transferring towards the delta load. So let us start with the IA is equal to 10 ampere, that is given. So as line C is open, so IC is equal to 0. Then we have the symmetrical component, so that's why IA plus IB plus IC is equal to 0. So in the IC we are putting 0 over here. So IB is equal to minus IA, so that will be minus 10 ampere. So we have mentioned over here IB is equal to minus 10 ampere. It was not given into the data, but after solving this we will have the value of IB, that is minus 10 ampere. Now symmetrical component of the line currents are that we have the equation that IA0 is equal to 1/3 of IA, IB and IC, IA plus IB plus IC. So put all the values of IA, IB, IC over here. So symmetrical component of the line current is say 1/3 of 10 minus 10, so it will be 0. So IA0 is equal to IB0 is equal to IC0 is equal to 0. Now let us calculate for the IA1. So IA1, for the IA1 we have the equation that is 1/3 of IA, 1/3 of IA plus alpha IB plus alpha square IC. Now we have all the values of IA, IB and IC, and alpha square. So yes, alpha is say 1 at angle 360, so it is 1, and then after alpha square is say 1 at angle 120, so it is mentioned over here. So 1/3 10 plus minus 10 into 1 at angle 20, and this is the term that is 0. So sorry, alpha is 1 at angle 20, and alpha square is over here, it is 0. So 1/3 10 plus 5 minus J 8.66. so after solving this we will have this value, and 1/3 is 1/3 into 15 minus J 8.66. So this is the A minus JB form of this IA1. So 5 minus J 2.8866, and the R angle theta form of IA1 is 5.77 at angle minus 30 ampere. So let us calculate the IB1 for this. So IB1 is say we are having IC is equal to 0, that's why this value we have put over here, that is 0. So IB1 is equal to alpha square into IA1. So we have the value of alpha square, that is 1 at angle 240, and IA1 is that we have derived over here 5.77 at angle minus 30 degree. So by putting this value we will have the value of IB1, that is 5.77 at angle 210 degree, and IC1 is alpha IA1. So yes, alpha is 1 at angle 120, and IA1 that we have derived y 5.77 into minus 30 degree, so it is 5.77 at angle 90 degree. So this is the value of IC1. Now let us calculate the value of IA2. So IA2 is one third of IA, one third into IA plus alpha square IB plus alpha into IC. So yes, one third into IA is equal to 10, alpha square is at 1 at angle 240, and IC is 0, that's why this term is placed over here, that is 0. So one third 10 plus 5 plus j 8.66. So after solving this, we will have that the value of a plus jb form, that is 5 plus j 2.8866. So ia2 r angle theta form of the ia2 is 5.77 at angle 30. Now ib2, that is alpha into ia2. So yes, alpha is 1 at angle 20, and ia2 that we have derived over here 5.77 at angle 30. So after solving this two, we will have the ib2 is equal to 5.77 at angle 150 degree, and ic2 is equal to alpha square into ia2, where alpha square is 1 at angle 240, and ia2 that we have derived over here, that is 5.77 at angle 30. So yes, ic2 is equal to 5.77 at angle 270 degree. So this is how we can solve the example related to the symmetrical components. Now after this presentation, you have the assignment questions. Two are the means theoretical question, and rest two are the calculative type means examples. So the first question is explain the symmetrical component of the symmetrical phasor with necessary diagram, and second question is derive the expression for the power in terms of the symmetrical component, and the third is the example, that is a delta connected balanced resistive load is connected across a unbalanced three-phase supply system, and the current is current in line A and B are say 10 at angle 30 and 15 at angle minus 60 respectively. Find the current in the C. So find out the symmetrical component of the phase value. So this is the example number 3, and the 4 is the voltage across three-phase unbalanced load are VA is equal to 200 at angle 40 degree, VB is equal to 320 at angle 190, and VC is equal to 48 at angle 340. So determine the symmetrical components of the voltage phase sequence in ABC. So yes, the instructions related to this assignment question is written below. Please read it carefully. You can take the snap of this slide also, and if you have any query and doubt, we can solve your queries and doubt in our doubt solving session, or if any further query arise in your mind, then feel free to call me to solve your doubts related to the electrical engineering. So thank you very much, student. Thank you all. Jai Swaminarayan. This is what in this presentation. Thank you very much all. Thank you, student. Jai Swaminarayan.